Okay, hi everyone. Welcome to our first lecture, Unit 1, which encompasses only one chapter, Chapter 21, where we will be talking about electric charge. What is electric charge? We're going to be talking about the forces that charges experience. And we'll also be talking about the electric field, which is something that emanates from a charge. Okay, and we'll get more into detail with those concepts. So let's start off by defining charge. What is charge? Well, charge is a property of matter, just like mass is a property of matter. The difference between charge and mass is mass, there's only one kind of mass, right? Charge, however, there's two different flavors, if you will. There's positive charges and negative charges. We can move charge around. We can charge things by in a couple of different ways, really. One way is to use friction, okay? Like, for example, rubbing a balloon on fur or hair, right? That creates friction between the rubber and the hair surfaces. And what that does is that releases charged particles and allows them to move around and be attracted to another object. And when we do that, we're left with an imbalance of charge, okay? And in the case of the cat and the balloon, what happens is that negative charges get unlocked from the fur by the friction, and they are attracted to the balloon and they remain on the balloon. And then when you bring those two objects, which now have a net positive and a net negative charge together, what you see is an attraction, right? An attractive force. And so that's just a demonstration of that property of charge. So one property of charge is that opposite charges attract each other. The second is that like charges, so two positives or two negatives, they will repel each other, okay? So that's kind of how we are going to start off a lot of new concepts. Is we're going to talk about the concept qualitatively. We're going to talk about the observations of this new concept, for example, charge. And then we'll get into kind of like the math and the nitty-gritty of it. So I gave you an example, right? Rubber from a balloon, fur from a cat, right? Those are two types of materials that when friction is generated between them, there'll be a charge imbalance and you'll have a net positive charge on one object, net negative charge on the other, and thus you'll have an attractive force, right? Because opposites attract. There's two other very textbook examples that you'll see in the book and in problems, and that's fur and plastic, which we kind of, rubber is kind of like a plastic, right? And silk and glass. So if you're, when you get to doing these kinds of experiments in your lab, you may see these materials being presented here. And so there really isn't like a formula or anything that tells you which type of material would prefer to attract negative charges and which would prefer to have positive charges accumulated on it. You just kind of have to memorize those. So don't worry too much if you're like, well, why does fur, lose negative charges or anything like that. So it's kind of by material, okay? And if you are interested, you can look up something called the triboelectric series. I'm just going to write that down here. The triboelectric series. It's kind of hard to write. I wonder if there's a typing. I'm kind of figuring out how to use this this recording technology. Triboelectric. Okay, if you want to just Google it, and you'll see a whole list of different materials and whether or not they like to gain positive charges or negative charges. Okay, and so let's talk a little bit more about this gaining and losing charges. Like, what do I mean by that? You may recall from chemistry um, the shell model of an atom, right? You have positive charges, also known as protons, in the nucleus, and then floating around the nucleus, along with the neutrons, you have electrons, and they can be understood as having shells around the nucleus, or clouds, or orbitals. Okay, those are all just different models of this same idea, right? The electrons are floating around outside of the nucleus, and therefore they can be easily moved, right? Because the positive charges, aka protons, in the nucleus, I mean, they're tightly bound in there, and there is no way to get them out without super high energies. For example, um, you know, putting these particles in a particle accelerator and slamming them into each other in order to release the protons. So, in other words, by simple friction of rubbing two items together, you are not going to release any protons, okay? Anytime you have simple conduction of electricity, what's moving around is the electrons, because they are not super tightly bound to the atom. They're floating around in orbitals or shells, or however you want to picture it. They're floating around outside and easily removed from the shell, right? In contrast to the nucleus, where you have protons and neutrons super tightly bound inside, not going anywhere without super duper high energy. So this is the reason why that whenever we talk about the movement of electron, or the movement of charge, what we're talking about is actually the movement of electrons. And this notion is going to be super important in a few chapters when we start talking about moving charges, okay? But for now, just know that electrons are the ones being the charged particles, right? Electrons are the charged particles that are moving around whenever we are transferring charge from one place to another. So let's illustrate how the movement of electrons either creates a positively charged object or a negatively charged object by looking at an atom or an ion. For example, right, neutral atoms, neutral objects have equal amounts of positive and negative charges. Positive ions or positively charged objects will have more protons than electrons. Negatively charged objects will have more electrons than protons. Okay, so you can extend that idea of an atom being positively charged or negatively charged to an object. So charge has a couple of other properties, okay, and they're kind of interesting. So the first one is that protons and electrons have the same magnitude charge, okay, and actually that value, 1.602 times 10 to the minus 19, right? You probably remember that from chemistry. That value is the smallest possible charge that exists in our world, okay? It cannot be divided up into any smaller pieces than that. We have not observed anything in this world that has a smaller charge than that. And because of that observation, because we can't find anything else that has a smaller multiple of 1.602 times 10 to the minus 19, we say that this charge is quantized, okay? Or this quantity of charge is quantized. And so everything in this world exists in multiples of 1.602 times 10 to the minus 19 coulombs. Everything that has a charge, that is, okay? So protons and electrons have the same magnitude charge, okay, opposite signs. That magnitude happens to be 1.602 times 10 to the minus 19. And the third property, my face is kind of covering. I don't know how to move the face around. when you can review these slides on your own without my face there eventually, is that the third property is that charge is conserved. So what does that mean? You've heard of like conservation rules from Physics 1, right? What does it mean that charge is conserved? Well, what that means is that anytime we're dealing with transferring charges, electrons or protons, if you will, are never created or destroyed. Like anytime that we're transferring charge from a rod to the fur or the balloon or whatever, those charges are not leaving the universe. They're just going from one object to another. And so what I'm saying is that every charge that ever existed in this universe today existed in this universe, millions of years ago, right? They didn't go anywhere. We're not aware of any other universes where these charges can move back and forth. So the conservation of charge is kind of a statement that the algebraic sum of all the charges in a closed system, okay, is constant. So you can move charges from circle guy to rod guy. Total number of charges is going to be 4, right? You can distribute it behind my picture here. Have 2 on the rod, 2 on the circle guy. Total charge is still 4. Okay? Charge is conserved. Okay, let's move on to the next slide. Not working. Oh, I see. Oh, my animations. Okay. I didn't realize the animations were. Yep, so there's my animations. So, so let's review kind of these concepts. All right. Which of the following statements are true? Statement 1, a neutral object contains no charge carriers. Okay, well, we know that's not true because a neutral object has equal number of positive and negative charges, okay, creating a net charge of 0. In other words, a neutral. So that's not true. 2, positive charges attract. We know that that's not true, right? Because opposites attract. Electric charge is conserved, right? We know that's true. We just talked about it, right? Charge is neither created nor destroyed. A positive charge and a negative charge attract each other. Yes. 2 negative charges repel each other. Yes. Electric charge is quantized. Yes. Okay, so let's talk a little bit more about objects, right? We were kind of looking at it from a microscopic point of view, looking at the charges on the atoms. Let's talk about these objects that we can classify according to how charge moves through them. So we define conductors as objects that allow charges to move freely through them, okay? For example, gold, silver, copper, right? Those are what we make, our wires out of because they allow electrons to flow through quite easily. Seawater is actually also a good conductor, and that's because of the minerals in seawater. What you may not realize is that pure water, okay, H2O without any things floating around in it, is actually not a very good conductor at all. Okay, and that's because of its dipolar nature. Let's talk about insulators. So insulators are objects that do not allow charge to flow easily through them. Okay, objects like rubber, okay, wood, glass, these things do not allow charges to move freely. That's why electricians wear big boots with rubber bottoms on them, right? To prevent, if they were to be shocked, it would prevent the current, which current is a flow of electrons. We'll learn that in a few chapters, right? It'll prevent the current from flowing all the way through them and damaging their body, okay? When you wear those big rubber soles on the bottom, that current is going to stop because it cannot flow through the rubber, okay? Because it's a good insulator. So now that we've talked qualitatively about the attractive and repulsive forces that charges experience when they're near each other, let's put some quantification behind that, okay? The strength of the force that 2 particles feel due to the other is given by the following equation here, which is called Coulomb's law. Okay, Coulomb's law is F equals K, which is a constant, times the value of each charge involved. Okay, so we denote little q as charge, divided by the distance between the two charges squared. So this r is just the distance between the two charges. Okay, so the magnitude of the force is given by this relationship here. Okay, it's called Coulomb's law. It's called electrostatic force. It's called Coulomb force. Okay, so you may see it referred to a few different ways. So the magnitude of that force, it's scaled by the magnitude of the two charges and also by inverse of the distance squared. Okay, it's called an inverse square law. You may have seen this before in gravitation. So force is a vector, as I'm sure you remember, right? And so this expression right here tells us the magnitude of that vector. Well, what about the direction, right? The direction is either directly toward, right, directly toward the other particle, or directly away from the other particle. So, right, depending on if they're both positive or negative. I can draw on my face, but can I move my face? How do I undo that? I don't want to draw my face. Maybe I'll draw a mustache. Sorry, I'm just being silly. So, because we're about to get into some fun math here. Where's my mustache? So, like I said before, just look at these slides again and you can move my face around. So anyway, right? So the direction is not assigned to an XY coordinate system unless we were to put those charges on a coordinate system, right? The direction now as we know it is either directly toward or directly away from the other charge. And so how do you determine what's directly toward and directly away? Okay, what does that mean? Well, if you draw a straight line between the two charges, okay, if you draw a straight line between the two charges, extending them out, toward or away will either be on that line towards the particle or on that line away from the particle. Okay, so no x and y yet, but we're going to get there, don't worry. We're going to get to I hat and j hat. But right now, we're just talking about the force in terms of directions directly toward or directly away. So I had a k as the constant, right? And you're probably like, what's k? What's k? Well, k is known as the Coulomb constant. But what it really is it's just a convenient way of writing this 1 over 4 pi epsilon naught factor, okay? 1 over 4 pi epsilon naught. That is the real proportionality factor, okay? And 4 pi, obviously, you know what that is. Epsilon naught, that is a physical constant that we call the electric constant. It's also called the permittivity of free space. And its value is right here, okay? But for ease of calculations, right, instead of typing 1 over 4 pi epsilon naught a million times, it's a lot easier to do k. And k comes out to be 9, if you just do to one significant figure, 9 times 10 to the 9. Okay, so that makes it real easy. So k is just a rearrangement of 1 over 4 pi epsilon naught. So I told you already, right, that the smallest possible charge in this world is 1.602 times 10 to the minus 19, right? Which is the charge of an electron, okay? We have, over the years, been measuring and trying to accurately, to many, many, many decimal places, find out what this value is, this quantization of charge. And this is just a kind of a fun graph that shows you, you know, for the past, you know, roughly over 100 years, how close and how close we've come to this value, and how our experimental methods have changed over the years, right? You can see big error bars, and now here you barely see any error bars. So let me just erase that. I need to use my laser pointer. There he is. There we go. Now you can see what I'm pointing at, right? You can see no error bars here. So just kind of fun, right? The other thing that this slide tells you is, right, so the units. What's the units of charge? Well, the units of charge are coulombs, okay? And a coulomb is actually a really big unit. So 1 coulomb is actually equal to about 6 times 10 to the 8 number of electrons, okay? That's a lot of electrons. So coulomb is a really big number. So when we do our problems, we're going to always be dealing with microcoulombs, nanocoulombs, even picocoulombs, okay? 10 to the minus 6, 10 to the minus 9, 10 to the minus 12, respectively. Okay, micro, nano, pico. So we're always going to be dealing with really small amounts of charge. So example 21.1, you guys should do and follow the video tutor example. I'm not going to do it with you guys because it's straightforward. I want to do some more complicated ones with you guys. So I'm going to skip this one, but you guys should do it just to kind of get a feel for the terminology, okay? This example relates back to gravity, right? What's the force of gravity? mg, okay? So it's a good example to kind of get you warmed up. So in your book, you're going to have some purple boxes kind of floating throughout the chapter. And these purple boxes are really good problem-solving strategies to help you solve certain types of problems. For example, this one is from Coulomb's law. So what I suggest you do is that when you're doing a homework problem for Coulomb's law, which would be find the force on this charge due to this charge, okay, those kind of problems, is to try to use this problem-solving strategy, right? Follow the steps and see how far it gets you before you get stuck, okay? I think it's a really good way to test your knowledge and test your ability to kind of like read technical directions and apply them to, you know, new and confusing topics. Okay, so this is the first example that I want to do together, and the way I have this example set up is it's all based on animations in the slides, okay? So the best way to get the most out of this example is to have your pencil and paper with you and follow along with the steps. So in this example, we're going to calculate the force between two charges, and the magnitudes of the charges are given here. 25 nanocoulombs for the first one and negative 75 nanocoulombs for the second charge, and they're separated by a distance of 3 centimeters. So what we're asked to find is the magnitude and direction of the force that Q1 exerts on Q2 and vice versa, the force that Q2 exerts on Q1. And so the way that you write this force with subscripts is 1 on 2 and 2 on 1, respectively. So the object that is feeling the force is going to be the second subscript, okay? So using Coulomb's law, we can plug in all of our values and get the magnitude of the force that charge 2 feels due to charge 1, okay? So we plug in all those values and we make sure that we convert the distance to meters, right? All SI units, centimeters is not SI. And we get 0.019 newtons, okay? Right, because it's a force, so the units are going to be newtons. And it turns out that if you were to do that same procedure for the force of 2 on 1, you're going to get the exact same number. Why? Well, because Q1 and Q2 are multiplied by each other, right? So they have the commutative property. So Q1 times Q2 equals Q2 times Q1, right? And they're both a distance of 3 centimeters away from each other. So the magnitude that the magnitude of the force that charge 1 feels due to 2 is going to be the same magnitude as 2 on 1. So that's all fine and dandy. Now, as we build our vector, right, we have figured out the magnitude. Now we need to figure out what the direction of that force is. So the direction is the next step. And so what I've done on this, what I forgot to mention is what I did on this example is I kind of took little pieces of that problem-solving strategy and put them with the parts of the problem if we were to go down along the problem-solving strategy and do each step. So the direction of F1 on 2 and F2 on 1, how do we determine that direction? Well, the rule is, right, opposites attract and like charges repel each other. So in this example, we have opposites, right? We have a positive charge and a negative charge. So the force that Q1 feels due to Q2 is going to be an attractive force. So it's going to want to move directly towards Q2. Okay, and so let's draw a little picture here. We're going to draw a free body diagram again, right? Remember that from Physics 1. And so for the subscript 1 on 2, so for the force that 1 exerts on 2, we're going to be drawing the free body diagram on 2, okay? That's how you would remember that. So, I have both free body diagrams up at the same time. So let's look at the first picture, right? I'm drawing the free body diagram on charge 2. It's feeling an attractive force to charge 1. So it's going to move in a straight line directly towards, let me get my laser pointer up here. It's going to move directly towards Q1. Straight line path, right? The most direct path possible would be a straight line connecting Q2 and Q1, so it's going to move directly towards Q1. We could call that to the left. Okay, that's the direction, to the left, right? We're not really in a coordinate system right now. We're just kind of describing the vector, okay? So the direction of F1, 2 is going to be to the left. So now let's look at F2, 1, okay? The force of 2 due to 1. No, I'm sorry, the force of 1 due to 2. So right, watch the language here, because in English, you can kind of, it's almost easier to describe it the other way than the way that the subscripts are, right? Let's look at the subscripts. F2 on 1. Okay, the force due to Q2 on Q1. So now we're going to draw the free body diagram on Q1, okay? They are opposite charges, so they are attractive, and so the direction of that force is going to be towards the other one, right? If they're attracted to each other, they're going to feel the force pull directly towards the other one, so the direction of that force is going to be to the right. Okay, so what if now we were to throw this on an XY coordinate system? Let's go ahead and describe those vectors in terms of x, positive and negative x, right? So by convention, x, positive x, on an XY coordinate system is to the right, right? Drawing that right there. There's a Y. So the direction of F1 on 2, right, is going to be in the negative I hat direction, right? I hat is what we use to denote the x-axis. And the direction of F2 on 1 is going to be in the positive x hat direction. I hat direction, sorry. Sometimes I say x. Positive I hat direction. Okay? So the magnitudes of those two forces are the same, but the directions are different, right? Because it depends on the frame of reference. Which charge are we talking about? So that's just a quick example. That example is going to be helpful in one of the pre-lecture problems, so be sure to revisit that. To the left and to the right. So this example I'm going to let you guys do. Follow along with the video tutor solution. If you click on that link right there, there will be a video that walks you through the solution, but go ahead and give it an attempt on your own first. That's going to be the best way to study. The best way to learn is to kind of like try it yourself. Get as far as you can before you are stumped and wasting a lot of time, right? Of course, don't, spin your wheels for hours and hours and let 2 hours go by. But give it a good go on your own, and then when you get stuck, look at the video or look at your resources, okay? So I'll let you guys do that one on your own. This is the example that I want to do together. Okay, so in this example, which is 21.4 in your book, we're going to be calculating the magnitude and direction of the total force on a charge, big Q, due to two other charges, Q1 and Q2. Q1 and Q2 are located on the y-axis, okay? And Q3 is a distance away on the x-axis. Okay, so let's go ahead and draw our sketch as mentioned in the problem-solving strategy, right? Sketch the locations of the particles and label them. Set up an XY coordinate system if they don't all lie on the same line. So this one's Q1, right? Because he's up here at plus 0.3. Q2 is down here at minus 0.3. And then big Q, which I'm going to call Q3, is at x equals 0.4 meters, y equals 0. Okay? So we have our positive charges. They're all positive. They're all laid out on the x-axis. And what we want to know is the total electric force that Q1 and Q2 exert on Q3. Okay? On Q3. Meaning our free body diagram is going to be on Q3. So let's go ahead and sketch out these vectors. Okay? Because we already know kind of what direction they should be based on the fact that opposite charges attract and like charges repel, okay? So if we take a look at 1 and 3, okay, how is Q1 going to affect Q3? All right, so if we draw a straight line from Q1 to Q3, okay, our force vector is either going to point directly toward or directly away from Q1. All right, well, guess what? They're both positive. So our force vector is going to point directly away along that line. Okay, that's going to be F13. F23, so the force that Q3 experiences due to 2, that's going to lie on that straight line path, and guess what? It's also going to be directly away because it's a positive charge. Okay, so we're just going to extend that line out and draw F23. Okay, so what we can do then to find the total, right? So our objective is to find the total force, which is going to be F13 plus F23. All right, so let's start off by finding F13. So F13, the way we find vectors in general, right, is to find a vector. We first determine its magnitude and then the direction, okay? So let's get the magnitude of the vector. That's pretty easy. The magnitude of F13 is going to follow Coulomb's law. Okay, Q1, Q3, divided by the distance between 1 and 3. Okay, So we know K, we know Q1, we know Q3. Well, what's the distance between 1 and 3? Let's go back and fill in some blanks here, right? This distance here is 0.3 meters, okay? This distance here is 0.4 meters. And the distance between 1 and 3 is going to be the hypotenuse of this triangle, okay, this right triangle right here. And it just so happens to be a 3, 4, 5 triangle. I don't know if that sounds familiar to you, right, from geometry. It's a special triangle, a 3, 4, 5 triangle. So I don't even need to use the Pythagorean theorem here. I am just going to, right off the bat, know that the hypotenuse is 0.5 because it follows a 3, 4, 5 triangle. So my distance then is 0.5 meters. So let's go ahead and plug everything in. Newtons per coulomb. Eggers, come on. Newtons meters squared per coulomb squared. Okay, Q1 is 2 microcoulombs. Q3 is 4 microcoulombs. Divided by the distance between 1 and 3, which was 0.5 meters, and then you square it. All right, so that gives us our magnitude of F13. I'm going to write it actually down here. Oops. That comes out to be 0.29 newtons. Okay, so there's our magnitude F13. All right, easy enough. What about the direction? Okay, well, the direction of F13, we can take a look here. It's got a component in the x direction, okay? And it's also got a component in the negative y direction. So we need to break this vector into components, all right, in order to get the direction. So we can break this vector into components a couple different ways, all right? I will briefly explain one way, and I will post a written solution of this example using that way. That way being the definition, chapter 3 definition of vector components, which was arbitrary vector A can be made up of magnitude A, cosine theta, I hat, magnitude A, sine theta, j hat. However, to use this formula, you need to be aware of how theta is defined, okay? So if this is our arbitrary vector A down here, like it is, like F13 is, okay? If this is arbitrary vector A, the angle theta must be defined as, that's theta, it must be defined as counterclockwise from the positive x direction, okay? So the angle that we give this formula, for a vector in the fourth quadrant, it's going to be a big angle, okay? Which may or may not be a pain in the butt to determine. So that's one way to do it. But if you do it that way, okay, if you choose to use this method, your signs will come out correctly, okay? Meaning you'll get that negative sign in the y direction, okay? So that's great. That's the nice thing about it is if you use this formula, your signs come out right as long as you provide the correct theta. So we're going to do another way. We're going to do it this way. So we're going to use similar triangles, okay, to find the components. And using the fact that the x component is positive because it points to the right and that the y component is negative. Okay, right? It's negative because it's pointing down. So let's treat, right? We talked about similar triangles. Let's treat this. This is just a right triangle right here, okay? This is the magnitude of that vector. And what we want to know is F13 and F13x and F13y. So we kind of need another piece of information, right? We need this angle theta. but we don't know this angle theta. We have too many unknowns in this triangle, right? The only known is F13 magnitude. We don't know F13x or F13y or theta, but we do know there is a similar triangle right here that also has theta, all right? You can see the similar triangles because this theta is coming off of the x-axis, and so is this one, okay? So that's how you know it's a similar triangle. When you're drawing your pictures without perfectly straight lines, it could be real easy to accidentally pick, you know, a different triangle. So just always make sure that your theta is coming off of the same axis, okay? So these two triangles here, this one and this one, those are similar triangles. They share that inner angle theta, all right? And we're going to use that to our advantage. So let's express, let's work on this triangle first, okay? And let's express F13x and F13y in terms of sine and cosine in that triangle. So I think I'm gonna work over here just so that we can have that picture still next to us. So F13x, F13x, all right, if this is a right triangle, F13x is on the adjacent side, okay? F13 magnitude is on the hypotenuse. What does that look like to you? Adjacent over hypotenuse. That's a cosine, right? What about F13y? Similarly, F13y, that's on the opposite of the angle. The hypotenuse being magnitude F13, right? Opposite over hypotenuse. That's sine theta. And we can solve for unknown. F13 magnitude, cosine theta. F13y is F13 magnitude, sine theta, okay? So we have a value for this, but we don't know what this is. We need to substitute something in there. And what we're going to substitute in there comes from the similar triangle where we have all the sides. So therefore we know exactly what sine theta and cosine theta is, okay? So using our similar triangle, where am I going to write that? Using our similar triangle, I'm going to draw it over here. We see that cosine theta which equals 0.4 over 0.5. A number, right? An exact number that we can substitute in here. And that sine theta is going to be opposite over hypotenuse. Opposite being the 0.3, right? It's opposite the angle. Okay? And we can substitute that right in there. And we get some values. So let me scoot over to the right here. Let's now write out our vector. F13 vector, okay? F13 vector has an x component equal to, right, F13 magnitude, which was 0.29 newtons, cosine theta, which was 0.4 meters over 0.5 meters, okay? What direction? Positive x direction, right? All right, what about the y? The magnitude of the y, F13 magnitude times sine theta, which is 0.3 over 0.5. So 0.29 times 0.3 meters over 0.5 meters in the j hat direction. Well, is it in the j hat? No, actually, it's in the minus j hat, right? It's pointing down. The y component is pointing down, so it's in the minus j hat direction. Okay, so that's, right, that's the caveat of using this method, right? Using this method, you get the values of the components, but you need to use your drawing to determine the directions if they're positive or negative, okay? Whereas in method 1, plugging in the correct theta will automatically give you the pluses and the minuses in the right place, okay? Do it both ways and see. So, so I had to make sure that I put the negative sign in there because the y component's pointing down, all right? Well, guess what? We did a whole bunch of work, and we got half of the problem, right? F13. What we also need is F23, right? So that we can add these vectors together to get the total force on 3. So we could do that. We could just kind of do all this business all over again, or we could kind of take a look at this problem and see if there's any symmetry to it to kind of reduce the amount of work we need to do on the problem. So what I want you to notice first is the magnitude of F23 and compare it to F13. So here's F13, right? Magnitude of F13 is KQ1 Q3 over R13 squared. Well, what about the magnitude of F23? Well, it's going to be K. Let me go ahead and write that down somewhere. It's right here, right? Let's go look at the magnitude of F23, K, Q2, Q3 over R23 squared. Well, guess what? It's going to be identical in magnitude to F13, right? Because Q1 and Q3 have the same value. Q3 obviously, I'm sorry, Q1 and Q2 have the same value. Q3 is obviously the same. And guess what? The distance between 2 and 3 is also 0.5, right? This is also 0.5 from here to here. So the magnitude of F23 is going to be the same as F13. So with that being said, if we break F23 into components, what you will notice is that, let me pick a color here, let's do pink, right? F23x is going to be to the right. F23y is going to be up. And we are going to see a cancellation between F13y and F23y because they are the same magnitude pointing in opposite directions, okay? And then the other thing we're going to see is that we're going to be adding together F23x and F13x. All right? So F23 is going to be it's going to have the same x component. We didn't write down what these values were. Let's go ahead and do that. 0.29 times 0.4 divided by 0.5. That gives you 0.23 newtons minus this becomes 0.17 newtons. Okay? So by comparison, our F23 is going to have the exact same x component, and the y component now will be the same magnitude but opposite sign, so it's going to have that plus. Okay, so now you can see when you add those two together, the y's go away and the x's double, so our total force is going to be 2 times 0.23 newtons in the I hat, which is 0.46 newtons I hat. Okay, so if that symmetry was hard for you to see, then what I suggest you do is to go through all the similar triangles, get those components for F23, and prove to yourself that it is the way I said it was, okay, that the y components cancel and the x components add. So that'll be a good exercise for you. So go ahead and try that. And of course, let me know if you have any questions about either of these methods, okay?